So today I'm going to present our recent work on applying on machine learning approach to designing mechanism for trading networks. So tomorrow, Sergey is going to give some more overview of the work that we're doing. So my talk is more like a single conference talk. Okay, so this is a joint work with Sergey and Elishva was our intern student. Okay. So this study is motivated by our question of how we can maximize the value that a trading network can produce under practical assumptions. So a trading network consists of companies who do business by trading with other companies. And each company has a choice of who to trade with, and this can be committed by making a contract with other companies. Here, a contract between a buyer and a seller specifies what is traded from the seller to the buyer and how much payment the buyer makes to the seller. So each company has the objective of maximizing its own utility, and its utility can depend on the trades and payments. So typically, those companies have conflicting objectives, but as a designer or mediator of a trading network, we would also want to maximize the social welfare, which is the sum of the utilities of those companies in the network. So this is precisely the objective of the prior work on trading networks. So they seek to find a set of contracts that maximizes the social welfare, the total utility of the companies. And this is so this can be done by a set of So this maximizing the total utility of the players can be shown to be equivalent to maximizing the total value that the trade induced by the contract for the companies. So that's shown here. So we say that a set of contract is efficient if this set of trade maximizes the total value to the companies. Okay, so more precisely, the goal of the prior work is to achieve a stronger property called stability. So a set of contract is said to be stable if the trade induced by the contract is efficient and a subset of the players cannot increase their utilities just by themselves. However, this prior work relies on the strong assumption that these valuation functions of the players are known. Okay, so here Vi is a valuation function of the company I, and it is a function that maps a set of trades to the value of the trades for that company. But in practice, those valuations are the private information of the companies, so they need to be reviewed or declared by the companies. Okay, then those companies can have the incentive to declare the values that are different from the true valuations. And here is a simple example. So here we have a seller who can produce a good at the cost of CS, and we have a buyer who can buy a good from the seller by paying some price, and add some value at the cost of CB, and sell the product to the market at the unit price of 1. Okay, and in this setting, so these are the utilities of the players. So there are many different ways to determine how to set this price P. But here now we can consider some fair pricing so that these two utilities becomes equivalent. So we just need to solve just one simple equation to find out that the payment, fair payment is this quantity, 1 plus CS minus CB divided by 2. Okay? With this price, we have these two utilities becomes equivalent. But you can see that this price depends on the cost. So this cost needs to be reviewed by the players. So so I use C hat to denote the cost declared by the players. Okay, but then these players have the incentive to declare the cost that is slightly higher than the true cost because this is the utilities by the utility that they get when they declare this cost. Well, however, if the cost of these two costs, the sum of the cost is higher than 1, then we should actually not conduct this trade, because the utility that we get with when the total cost is high, then the utility becomes negative, which is smaller than the default utility of 0 that they can get without any trading. Okay? So this means that the players have the incentive to declare the cost that is higher than the true cost. But if they declare the too high cost, then the trade is not conducted, and which this leads to inefficiency. Okay, so what we want to do is to promote truthfulness. And we do so by introducing some independent party and allow a payment between these players and independent party. And then we can think about this these mechanisms. Okay, first we let players declare their valuations, and depending on the declared valuation, independent party determines the set of contracts to make, and also the payment between players and independent party. And all of these can depend on depend on the declared valuations. Okay, so the mechanism can be specified by three rules. The first rule is called allocation rule, and it determines the set of trades to be conducted. Okay, and the second rule is called payment rule. And this payment rule determines the payment associated with each trade. Okay? The third rule is also called payment, but this rule determines the payment between players and IP, independent party. All right. So we want to design a mechanism that achieves the 4 properties that are listed here. So I'm going to explain each of these properties. So the first property is called dominant strategy incentive compatibility, or DSIC. Okay? And this means that so under this mechanism with DSIC property, that the best for each player, the best strategy is to be truthful, to tell the true valuations. And this is regardless of the strategies of other players. So it is a very strong property for to guarantee truthfulness. And second property is, of course, efficiency, which is originally what we wanted to achieve. This means that the total value of the trade is maximized. Right? So these are the kind of basic properties that we wanted to achieve. So we wanted to promote truthfulness to achieve efficiency. But those are not sufficient in practice, and we also want to achieve these other properties. So weak budget balance means that the independent party has non-negative utilities. But independent party that doesn't it's not involved in any trade. So it just means that the net payment to independent party should be positive. So IP should not invest for this trading network. Okay, so individual rationality means that every player has non-negative utility. Otherwise, if a player doesn't have get a positive utility, there is no incentive to be a part of the network. So these are also a kind of necessary property for the trading network. Okay, so these properties are actually a standard in the literature of mechanism design. And for combinatorial auctions, it is known that VCC mechanism with Clark pivot rule can guarantee all of these four properties simultaneously. So you might expect that we can also achieve these four properties in trading network. It turns out that it is not possible to achieve all of these properties. Okay. So yeah, and here is an example. So we have, again, we have just only two players, so seller and buyer, and we have just a single good to trade. And suppose that each player is either one of two types, low type or high type. When the player has low type, it means that the player has low valuation on the trade. And high type, H type, means a player has high valuation on the trade. And we can show that it is impossible to achieve all of the four properties when we have this condition shown in the table. So let me explain this table. So if the two players have low valuation on the trade, then we should not conduct the trade. Okay, because both of the players have low valuation on the trade. So why do we want to do the trading? And for all of the other cases, we should conduct the trade. And it means that for all of those cases, some of the utilities or some of the values is non-negative or positive. Okay, so it is a very reasonable cases. But we can show that for all of the cases that satisfy these conditions, it is impossible to achieve all of the properties. And here I say ex post. So ex post means that for all cases. So it means that there are, in this case, we have four possible type allocations, types, four possible combination of types. And it is impossible. So it might be possible to achieve the four properties for some of the cases, but it is not. It is impossible to achieve the four properties for all of the four cases. Okay. Oh, by the way, I am also happy to be interactive, so I'm happy to get you. Please.
What is the key difference here compared to a combinatorial auction where you can solve it? Is it because there's both a buyer and a seller?
Yes, and more technically, in this case, so a player can have negative valuations, and for combinatorial auctions, all of the valuations are positive. Yeah. Okay. All right. So it is impossible to achieve all of these four properties, and this motivates us to make some compromise. So we're going to relax some of the properties. So here we relax the properties from ex post to in expectation. So now we assume that the types have some prior distribution, some distributions. And we assume that we seek to achieve these two third and fourth properties in expectation rather than ex post. But we want to achieve the first two properties still in ex post. Okay? So one detail is that so we assume that every player knows its own type. So this expectation is conditional on the valuation of my own valuations. All right. So So to design the mechanism that satisfy these four properties, we're going to take an automated mechanism design approach. And here we consider two approaches. One is computational, and the other is learning. For computational approach, we assume that the prior distribution of the types is known. And we're going to discuss some of the shortcomings of this computational approach, and then propose this learning approach that mitigate some of those shortcomings. Okay, so here is some kind of basic property that we can use. So I say that the mechanism can be specified by three rules: allocation rule and two payment rules. But it turns out that for the trading network, we don't need to consider the payment between players. And this is a simple reason for this important property. But suppose that we need to make a payment from this player from the buyer to seller. But we can do the same thing by letting the buyer to pay to the independent party, and independent party pay the same amount to the seller, and these are equivalent. So in trading networks, we don't need to consider the payment direct payment between players. So we only need to only need to design allocation rule and the payment rule between player and independent party. Okay, so here is so now I can talk about our approach. So we wanted to guarantee these four properties. And to guarantee the first two property, we're going to leverage a class of mechanism called Groves mechanisms. So our mechanism is said to be a Groves mechanism when allocation rule and payment rule has this structure. So the allocation rule simply says that we should allocate a efficient set of trades, which maximizes the total value of the trade for the companies. And payment rule consists of two parts. And first part is just so this is the payment from company I to independent party when we represent the valuations declared by the companies. Okay. So HI is just an arbitrary function, but it is a function of the valuations declared by other players. Yeah. And this the second part is just sum of the value of the efficient set of trades to other companies. So I say that the HI is just an arbitrary function. So so we have the flexibility of choosing what function we should use to achieve the third and second properties. So and H is called a pivot rule, and this is our free parameters. And now our goal can be specified, can be said as we can choose the right function H to achieve to satisfy the remaining properties of weak budget balance and individual rationality and in expectation. Okay, so here is the kind of optimization problem that we want to solve, that we can solve to find the right function H. And here, the variable of this optimization problem is the output value of the pivot rule. So HI V minus I. So V minus I is the valuation declared by other companies other than I, right? Okay, so this HI V minus I is the variable in this optimization problem. Okay, so we have So and we have these two types of constraints, and these constraints corresponds to each of these two properties. The first constraint corresponds to the weak budget balance, and it holds in expectation. It guarantees that it holds in expectation. And the second constraint says that the individual rationality holds for all players having all types. For every player of every type, this expected utility should be non-negative. That's the second constraint says. So and the objective function can be please.
So for v minus I, is it only corresponding to the seller? Like if you consider I is the buyer, is the seller, will v minus I only be the seller, or it can be other? So right now it's like a 1 versus 1 scenario, right?
Okay. So the contract is bilateral, so it is a contract is between two players, but we consider all of the players. So with v minus I, so minus I includes all the companies except mine.
So it includes both buyers and sellers.
Both buyers. So so every company can be both buyer and seller simultaneously, because a company can buy something from other companies, produce something, and sell it to the market or other companies.
It's like a directed graph.
Directed, yes.
You can have edges coming in
Mm-hmm.
and edges going out.
Yes. Okay. So the objective function can be arbitrary, but here we chose this objective function. It means that we want to make this budget balance as strong as possible, which means that so together with the first constraint, it means that we want to minimize the utility of our independent party, but we want to make it, but no smaller than 0. Okay, so we want to make the profit of the independent party as small as possible, but not smaller than 0. Okay, so that's our objective function and first constraint. So this is a linear program. If we have only a finite number of players and a finite number of valuations, or finite number of types. So, but it can have a very large number of variables. So for many cases, it is computationally intractable. But for small instances, we can actually solve this problem. So, okay. So here is first. So we apply this computational approach to this setting. So this is an example that I showed that it is impossible. So in this example, it is impossible to achieve all of the four properties ex post. But our goal is to find the mechanism that achieves four properties where two of them is relaxed to hold in expectation. Only 5 minutes. Okay, let me try. Okay. And in this setting, we generated random instances and applied our computational approach. And here is the result. So we generated about like 1,600 instances, and for all of those instances, we were able to achieve a budget balance in expectation. And not only weak budget balance, we achieved a strong budget balance. Okay, and for individual rationality, we also achieved individual rationality for all of the players and with all of the types in all of those instances. So it is actually possible to achieve the four properties when two of them is relaxed in expectation. Okay, so this computational approach has some shortcomings. So one is that we can have infinitely many variables. When we have infinitely many possible valuation functions. And in practice, it can have infinitely many valuations, right? And it also requires the exact knowledge of the prior distribution of types. So that's why we also want to consider this learning approach where we use functional approximation to deal with infinitely many variables and just use sample from the distribution. Okay, so I think I don't have time to explain details, but we replace H with some machine learning model having a finite number of parameters theta. And we use sample instead of the exact distribution. And this is some minor details, but we also need some other techniques. Okay, and we apply this learning technique to the same instances. And here the x-axis now shows the number of samples. Okay, we use. So it means that these results show that as long as we have a sufficient amount of the data, the learning problem has feasible solutions, and for optimal solutions satisfies all of the properties with high probability. That's this the result shows. Yeah, that's in words. Okay. So here, so one caveat in this learning approach that so we are learning this pivot rule HI, but this one difficulty is that this is a function of functions. So valuation function is an input to the pivot rule. So there is a question about how to represent those input to the function. So, but each function can be specified by its output values. So here we consider all of the possible input to this valuation functions, and consider those output corresponding to the inputs. And these output values completely specifies these valuation functions. So this HI function HI can be considered as a function of all of these output values. But the problem is that we have exponentially many output values. Okay, so we also, I'm going to skip the details, but we also come up with some ideas to reduce the number of input variables. And for that purpose, we manually designed some special growth mechanism that satisfies three of the four properties exposed, and it is guarantees. And these special growth mechanisms is used as a guidance to what variables can be eliminated from the input. So we have reduced the number of input from exponential to linear in some way, and apply the same problem with this reduced variables. And we find that it is still possible to achieve all of the four properties when two properties are relaxed in expectation, even if we use only a linear number of variables. Okay, so I think I was just a very quick summary. So we have kind of two types of results. One is impossibility, and the other is kind of a possibility. So we have shown that for trading networks, it is impossible to guarantee all of the four properties for all trading networks. Okay, and this is very different from what is known in combinatorial auctions. And for possibility, we have proposed a computational approach and a learning approach to find a mechanism that satisfies four properties, but where two of them is relaxed to hold in expectation. Okay, so I think I'm going to stop here. I prepared some detailed slides that compares our approach against some of those prior works, because I ignored most of the prior work in the talk. So, yeah. Okay, so let me, please. Okay, that's it. Thank you.
Questions?
Please.
I was just wondering kind of applications you have in mind? Like lots of times when people are negotiating, I don't know, agents or whatever, negotiating with one another, is it realistic to think that we could just have a third party come in and say, oh, talk to me instead of negotiating amongst yourselves, especially like in a large trading network?
Yes, I think that is a possible the direction to think about. So it is related to this part of indirect mechanisms. So yeah, we are thinking about such a supply chain scenario where the companies get together and possibly do some negotiations. So in this talk, I talked about the direct mechanism, where in the beginning, the companies have to declare their valuations, and in the part they decide everything, and that can be kind of that may be some too complex. So it might be a good idea to do some indirect mechanism where we allow the companies to negotiate with each other. So during the negotiation, the companies gradually reveal their information and finally agree on the price or something like that.
So are you viewing this study then as more like a baseline, like something what you could do with this extra third party, but maybe we'll then try to achieve something similar without?
Yeah, that's what we want to achieve. Yes. Yes, please.
A question related to Amy's. Just your definition of individual rationality. I mean, with this third party might extract some payment for the service, right?
Yeah.
And it seems to me that these two parties could just negotiate with each other and get greater utility. So it's not just non-negative utility. It's they have an external option where they could, hey, maybe we could do better just negotiating amongst ourselves, third party, be damned. Is that kind of captured? I didn't quite get the picture. Is that captured in your scenario?
I think it is captured, but what do you think?
So so parties could collaborate and get better, but for example in supply chain, that's exactly the problem of double marginalization, where the equilibrium is less efficient than the welfare. So what happens is that if each party tries to maximize their own utility, they actually end up in a scenario where they both get worse off than if they collaborated.
No, I understand, but I'm thinking of a scenario where, no, we're certainly not efficient, right? Maybe we're not efficient, right? But we're both better off because we're avoiding interacting with
but I'm saying the other way around. Because you're not efficient, there's always a scenario where you add a third party where both can get more. The third party may get very little, but they can still get something.
No, but my question is, will the third party get very little and ensure that we satisfy these properties?
That's a separate question.
That's
but at least there can exist a third party.
There exists, right. Yeah.
Yeah.
So following up on Greg's point on Amy's point, so it seems that whether the third party can be helpful depends on what contracts the parties can make themselves.
Right.
Like in the normal Myers and Satterthwaite trading situation, the most efficient mechanism is that each of us write our value on a piece of paper, and if the buyer's valuation is higher than the seller, they trade at the halfway point of that, and otherwise they don't trade. And the parties can simply agree to do that, and then the third party can't contribute anything.
Is that a question or just?
Well, it's kind of a following up to that answer, that there's always something that the third party can do to make the parties better. But in that example, if they themselves can agree to that type of a simple mechanism, there is nothing that the third party can add.
Right, but so what about our impossibility result? So we show that it is impossible to guarantee the four properties.
Well, that's what Myers and Satterthwaite proves in a slightly different setting. But in a Myers-Seller setting, that's what Myers and Satterthwaite already proves.
Yes.
And the optimal mechanism, which is inefficient, is the one where they both write their valuations on a piece of paper and trade at the halfway point if the buyer's valuation is higher.
No, the optimal value is efficient. That's exactly what isn't the optimal value efficient? The optimal when you say optimal, isn't it optimal in terms of efficiency?
Well, it's optimal in that it's best, but it's not efficient because efficiency is impossible. So it's going to be inefficient because they're going to lie in equilibrium, and sometimes the item is not going to trade when it should. That's where the inefficiency comes from. But if they can, if they could themselves just agree to that, we're going to write out valuations on pieces of paper, and then if there's room for exchange according to those numbers, then we exchange at the halfway point. That is the most efficient mechanism that you can achieve with a third party or without.
I think maybe we should take this offline, because I think it depends on what we mean by efficiency and optimality.
Okay.
So just very quickly, I guess I saw this flash by, but it relates to what Thomas was just saying. I guess I'm curious as to what is the technical difference? Why doesn't your impossibility theorem follow directly from Meyerson-Satterthwaite? Like, what's going on that's actually different here?
Yeah, I prepared that. That's no, yeah, this one. So it is not that different, but so we have two differences. So Meyerson-Satterthwaite theorem is on with Bayesian-Nash insensitivity compatibility. So and ours is with DSIC. So in that sense, they have a stronger impossibility result. But they assume some continuous they assume that the distributions are continuous, and the proof relies on the properties of the density functions. And we do not assume anything about continuity. So our impossibility results holds with even for the discrete cases.
So then, so the universality of the impossibility of Meyerson-Satterthwaite assumes the continuous distributions. So if you have continuous distributions, then it doesn't depend on the distributions. Then for all distributions you have inefficiency or impossibility of the form. Well, in 3 of the case. But are you saying that your impossibility is also universal, that it applies to all priors? Because that's hard to believe. And if it's not universal, then the continuity doesn't matter, right?
So if universal means that it is for all the distributions?
Yes, that's what I mean.
Yeah, I think our impossibility is universal.
But what if you have point distributions? There's no two-sided uncertainty. You don't get possibility there.
Then I think that is. So
I think, but isn't it the other way around? I mean, when Meyerson says continuity, it says continuity about. It says that if I need to assume that and this has to be the last question. If I have to assume, because making people late for lunch, making you late for lunch. If we have to assume that the buyers and the parties can be taken from any continuous distribution, then then it's impossible to guarantee for all continuous distributions. What we're saying is that we're now restricting to just discrete distributions, and even if we need to limit for all discrete distributions, even there it's impossible in this setting.
So that's not what the Meyerson-Satterthwaite says. It says that as long as you have overlapping distributions, then it applies to all continuous distributions.
Okay.
So there are some conditions that it needs to have the conditions specified by this table. So in that sense, like point mass doesn't fall into that doesn't satisfy these conditions. So yeah, so maybe it's not universal, I guess.
But in that sense, it seems similar. Your thing seems similar. The Meyerson also, if you allow point mass, they don't have overlap, then it doesn't. It's not universal, but it's universal among all the things that are continuous and overlapping. So anyway.
So maybe we should probably take this offline to see if we need to improve our results.
Yeah. Thank you very much.